Welcome to lesson 4, the final lesson from chapter 8, parametric equations from year 2 pure maths. And today we're going to look at how to apply parametric equations to modeling situations. So we're going to combine all the skills that we've developed over the past few lessons, and we're going to see how they can be applied in real life situations. All right, please pause the video and try the 4 warm-up questions. Okay, and let's have a look at the solutions. So in question 1, we're given 2 parametric equations for x and y, and the parameter t is defined for all real numbers. And notice that we have an exponential function here. What we're asked to do is to find the value of t when x equals 0. And of course, just to remind you, when x equals 0, this will give us the y-intercept. Okay, now there may be more than one, so I'll just allude to that by putting the s in brackets there. So any y-intercepts occur when x equals 0, and similarly, we have x-intercepts, which we call the roots, don't we, when we're talking about quadratics specifically. They occur when y is equal to 0. So there's that similarity there. Now, to find out the value of t in each case, it's quite straightforward. So for part A, if I set x equal to 0, then my equation for x will simply be 3t squared subtract 1 must be equal to 0. And you'll notice this is quadratic, so this will give us 2 possible solutions for t. So if we rearrange this, we have 3t squared is equal to 1. So t, or t squared, would equal 1/3. So t would equal 1 over, sorry, just do that again, plus or minus 1 over root 3. Okay, now notice it says find the value of t. It's probably a mistake that it should say the values of t when we have these particular situations. And both values of t are valid because t can be any real number, as we can see here. So that's the first one. So we have 2 values of t. So that suggests that there are 2 y-intercepts in this case. Now, for part B, in fact, let's just make a note of that. Just so we're clear, because we have 2 distinct values of t. We've got the two y-intercepts. So for part B, we're going to set y equal to 0 now. So when y equals 0, we set our y equation equal to 0. So we know that e to the power t subtract 1 will equal 0. So this means that we have rearranging, making e to the power t the subject, e to the t is equal to 1. Now, we can take natural logs of both sides here. So we'll do that, applying the log function. So the natural log of e to the power t. Remember, you take natural logs of the entirety of the left-hand side and the entirety of the right-hand side. You do not do it term by term like you would do with differentiation. Okay, so I've applied the log function to both sides. The natural log of e is an inverse, are inverse operations. So that just becomes t essentially, because the t will come down to the front. And the natural log of e is just 1. And the natural log of 1 is, of course, 0. So that means that t is equal to 0. Once again, I mean, you can check your answer by substituting back in. So we have 1 distinct value of t here. So that means we just have the 1 x-intercept. So there's a lot of information locked in this. We can find out what those x and y intercepts are by subbing our values of t back into our equations. As you'll know from experience now, when we sub in our values of t here, this would generate an x coordinate, and subbing a value of t in here would generate a y coordinate. Okay, moving on to question 2, we have a curve C defined by the function f, and this function f is a quadratic. Now, there's plenty of information locked in this form of a quadratic. This is in completed squared form, so I can look at that and determine several things. The 2 at the front is a scaling. Okay, so it's not going to cause us too much issue, even though it makes it a little bit harder to work with you under normal circumstances. But what is interesting is we have the x plus 4 all squared. So if I set that equal to 0, I'll get onto the range in a second. That means that x would equal -4, and this is the equation of the mirror line. Remember, quadratics are always symmetrical. So the line of symmetry has an equation x equals -4. So that's locked inside the quadratic when it's in completed squared form. We also know something else. Because this is a positive x squared term, when we multiply out all this, we would have 2x squared. This tells us that the quadratic, because it's positive x squared, it has a U shape, so it's going to be like that. So this tells us that it has a minimum value. Now, the minimum value is staring at us as well. So we know that if the x plus 4 all squared, whatever value of x you sub in, doesn't matter, you're always going to get a positive number. The smallest number you can ever get is 0 when you sub in x is equal to -4, which we've just deduced right here. So that means that the smallest that square bracket can be is 0, which means that subtracting 5 would make the minimum at -5. So we know from just looking at it, so we've got the +4 there and the -5 there, we know that there is a minimum, which I'll just write down at the coordinates -4, -5. Okay. Now, how does that help us find the range? Well, because we know that it's a minimum point, hence the range means that because the x values can be any real number, we can put anything in we want. The y values have to be greater than or equal to -5. And y would also be a real number as well. Okay, so I hope that makes sense. A bit of revision on quadratic properties. All right, now in part B, we're going to change the domain slightly. We're going to restrict the domain so that x is strictly less than -4. Now, if we do that, notice this number has probably been chosen for a reason. Strictly less than -4. Remember, x equals -4 is the mirror line. So we could just sort of sketch what's going on here. If I just put the quadratic on here like this, and we put x is equal to -4, that equation there. And we know it has a minimum at -5, so there'll be some x-intercepts along here. All right, so what happens to the range? Well, we know that the y value right here at that minimum point is -5. So if we allow the domain to be restricted, so that we're only including values less than -4, strictly less than -4. That means that the range is going to be affected ever so slightly. So the range is going to be anything strictly greater than -5 because that minimum point is now excluded. So let's just make a note of that. So the minimum is now excluded. I'm just putting that in inverted commas. I'm not using mathematical terminology there. Okay, so the range was almost the same because we're just taking into account the left-hand side of the minimum. So y would have to be strictly greater than -5, and y would be a real number still. Okay, so just be aware, restrictions on the domain have effects on the range. Okay, now question 3, we're going to be revising some differentiation, and we've got a diagram here of a rotated ellipse, a curve C, which hasn't been labeled. I'm just going to label that. So this is the curve C here. There are 2 points of interest which we're going to look at in question 4, which is at A and B. But before we do that, we are asked to find dy by dx in terms of x and y. Well, if we look at this expression, this equation, I should say, term by term, we can differentiate most of it normally, okay? But if we just focus on the term xy plus xy for a second, that's a problem because we have 2 variables multiplied together. They're not the same variable. We're going to have to use the product rule for that bit. But everything else we can differentiate as normal. The other thing to bear in mind, of course, is we have a y variable here. That's going to require implicit differentiation as well. So this is an exercise in implicit differentiation. All right, so let's just number or label these. So we've got A, B, C, and we'll call that D. We're going to do A first. Well, if we differentiate A, that's just going to be 2x. Now for B, finding the derivative of xy, so I'm just going to call this function u. So let u equal xy. Now, our task is to find out what du by dx is. We need to differentiate the product xy. So this is where we use our differentiation techniques for implicit differentiation. So if I call that 1, I call that 2. So we're going to set it up. So we're going to have 1, diff 1, and 2, diff 2. And we can use the product rule to differentiate the expression on the right-hand side. So 1 is, of course, x, and 2 is y. If I differentiate x, obviously this is always with respect to x, I just get 1. If I differentiate y with respect to x, I have to differentiate but also multiply my derivative by dy by dx because we're using the chain rule. And I did just mention it's obvious that we're differentiating with respect to x. Well, that's because we're finding du by dx. So using the product rule, so we can say du by dx is simply going to be, start with the bottom left-hand corner, which is how I tend to do it. So start with that one and then cross multiply essentially. So it's going to be y plus x dy by dx. Okay, so that's that part differentiated. So that's just part B. The rest of it is relatively straightforward compared to that. So I'm just going to borrow a bit of space from question 4 here, simply because I don't have much room on the board at this present time. So I'm just going to borrow that space. All right, so let's put it all together. So differentiating the whole thing. So term A, we're going to get 2x. So that's that one done. Okay, now term B, we've just done that. I called that the function u. So I said let u equal x, xy. We've differentiated that. So we just have to add what we've just found. So that's going to be plus y plus x dy by dx. Okay, so that bit's done. Then we have to differentiate y squared. Now we've got to be careful here. This is implicit differentiation. So I can differentiate as normal. So it's plus 2y, except that I need my dy by dx. If you need to revise this, go to the lesson in differentiation on implicit differentiation, and I explain why we use dy by dx as an extra factor. Then if we differentiate -1, so that's that one done, we just get 0, so it's a constant. So and then differentiate 0 on the right hand side, and we just get 0. So just for completeness, you differentiate every single term. So we could call that term E, and then that goes to 0, and that is still 0. Okay, so the whole of that equation has now been differentiated. However, it does say find dy by dx in terms of x and y. So we now make dy by dx the subject. Again, use the space you've got below for this. Okay. All right. So anything that doesn't contain a factor of dy by dx, I'm going to move that to the right hand side. So I'm going to subtract 2x and subtract y from both sides. So we're going to get x dy by dx plus 2y dy by dx. Okay, it's going to equal negative 2x, subtracting the 2x on both sides, and subtract y. Now, I can factor out the dy by dx from the terms on the left-hand side. So we have a common factor of dy by dx here. I can just factorize that. So let's take that out. So we have dy by dx multiplying x plus 2y, close the bracket, and that's going to be equal to negative 2x subtract y. And to complete this question, we just have to divide now by x plus 2y. So therefore, dy by dx is going to equal negative 2x subtract y over x plus 2y. So we now have an expression in terms of x and y for the derivative dy by dx. Right, so that's quite a complex process. All right, expect that kind of thing in an exam situation when you're using implicit differentiation. So moving on to question 4, it says find the exact x coordinates of the points A and B shown in the diagram in question 3. Well, we have to consider what's happening to the gradients at those points. Now, if we just for a moment just consider the opposite situation, where we would have, let's say, a straight line across there. I'm just going to put that more in position. So a straight line there. We would see that the gradient at this point, dy by dx, would equal 0. I think that's pretty clear. Dy by dx along there would be 0. Similarly, if I drag this horizontal line to the bottom, we'd also have a similar situation. The dy by dx would be 0 at that point as well. Now, when we have perpendicular lines, those lines are usually denoted as an x equal to some constant. So they don't actually have a gradient as such. But if we consider what happens with gradients as they increase in steepness, we can see the following. So if I take an ordinary straight line and measure the gradient of it's just the change in y of the change in x. As we make the line steeper, so let's say something like that, the change in y is going to increase. Okay, if we keep the change in x the same, the change in y is obviously going to increase. And when we get to the situation where we have a vertical line, then if the change in x is the same, then the change in y is never going to be accounted for. So we could say that the change in y is infinite. Now, if the gradient measures the change in y over the change in x, and this change in y is infinite, which is not a number, it's just an idea, then to create an infinite gradient, or a gradient that is undefined, which is more accurate to say, then we have to make this gradient that we have on the right hand side over here, the one I'm talking about, we have to somehow make this gradient undefined, because they are vertical straight lines. Now, to make it undefined or have an infinite gradient, if you like, an infinite steepness, the way to do that is, of course, to set the denominator equal to 0. Okay? If you set the denominator equal to 0, that would make your gradient undefined, and it would be a vertical straight line. Now, looking at the yellow line that we talked about earlier, where it's a horizontal straight line, you would just simply set your dy by dx equal to 0. Now, you'll notice that the denominator can never be 0. So in that situation, you would just set the numerator equal to 0. That would render the entire gradient equal to 0, and you would get the gradient of the horizontal straight line. Okay, so I hope that makes some sort of sense. So we have to set our denominator equal to 0 in this situation. So by doing that, if x plus 2y is equal to 0, what that means is if I'm asked to find the exact x coordinates, I need to substitute an x value or the x variable in for y wherever I see it. So that means that if I make y the subject, we have 2y would equal to negative x, which implies that y would equal negative x over 2. So the situation where we would have an undefined gradient, a vertical straight line, basically, if you drew a tangent to it, that would occur when the y values are equal to the negative version of the x value divided by 2. So we have to sub this in to our original equation. Okay. So I'll call this asterisk. So we're going to sub that into our original equation. And then we'll have the points on the equation where this is true. So if we sub our star asterisk in the equation. Again, I mean, I know this is a warm-up. This is a challenging question, but it's something I want you to be aware of. It's worth doing at some point. So, okay, let's have a look. We've got x squared, so that doesn't change. Plus xy. Now, we've got x multiplied by y, which is now negative x over 2. Okay. And then we have plus y squared. So that's going to be, just plug the brackets in again. So that's going to be negative x over 2 and then we've got to close the bracket and square that. All right, and then subtract 1, and we set that equal to 0. All right, now we just have to solve for x now, essentially. And it's not as bad as it looks. We're going to get x squareds all over the place here. So therefore, and this is, of course, question 4. I should just stipulate that because I continue question 3 on the right-hand side. So let's just put all this together. So we've got x squared, subtract x squared over 2, multiplying through. Now, squaring negative x over 2 is just going to make everything positive, and then we're adding that. So plus x squared over 4. And I'll put the 1 on the right-hand side. I'll add 1 to both sides. So what do we have here? Well, we have got essentially 1x squared, subtract a half. So that's 1x squared, which gives us a half x squared, and add a quarter. So that's going to be 3/4 x squared is equal to 1. All right, and I'm just again running out of room. These questions are quite involved, aren't they? I hope that makes sense. Just collecting all the x squareds together. Multiply by 4 and divide by 3. Okay, and we know we've got 2 coordinates to find. We've got the points A and B. So we take the positive and negative root. So x would equal 2 over root 3. I'll just leave it as that for now. Or x would equal negative 2 over root 3. Okay, and you can rationalize those if you like. So we can see, hopefully from the diagram, which one's which. We have a negative and a positive, and they are equidistant from the y-axis on both sides. So that makes sense. It seems to fit what we see in the diagram. So it looks like B is at the point negative 2 over root 3, and then there'll be some y coordinate here. I'll just call it YB. We don't know what it is. We could find that out if we wanted to. All right, and then the A would be at 2 over root 3 and some y coordinate for A. Okay, so just be mindful of that. Infinite or undefined gradients. Okay, if you have a dy by dx like you have here, where it's given as a fraction, for the horizontal straight line tangent, where dy by dx is 0, set the numerator equal to 0. If it's a vertical tangent, then set the denominator equal to 0, and then just proceed. Okay, so that concludes the warm-up. All right, so our first worked example, we have a projectile situation. So we have a stone thrown from the top of a 25-meter high cliff. And we've got a diagram here to assist us with this. Now, what I'm going to do is I'm going to redraw the diagram just to give us first a bit more space, and then just to remove any unnecessary sort of background noise with the illustration, and just focus purely on the maths and the parabola itself. So we're given some information. 25-meter high cliff, and you can see that in the diagram here, labeled clearly. It's projected with an initial speed of 5 meters per second at an angle of 45 degrees. This is something we're going to look at in more detail when projectiles is covered in the applied part of the course, chapter 6 in mechanics. So the important information is to follow. So it says its position after t seconds can be described using the following parametric equations. So those equations are given to us. Now, what is not given is this value here, k. K is a constant, but we need to be clear about how x and y are defined. That's absolutely paramount, because it's not necessarily going to be in every situation that x is the horizontal distance traveled and y is the vertical distance traveled. not necessarily the case whatsoever. So we need to read the definitions of x and y really carefully. So in this situation, x is the horizontal distance from the point of projection. Now, if I just add that to the diagram, I'm just going to put an x-axis on here. If you'll notice, the point of projection occurs round about there. So my positive x-axis actually is going to start where I'm putting this red line right now. So if I just label those, so this would be your y-axis. Your origin would be right here, and your x-axis would be right here. Now, there's loads of modeling assumptions when we're doing this. Obviously, you're assuming that the vertical height is indeed straight, so there's no sort of deviation. There's no angle. It's literally right on top of the origin where the point is projected from, and obviously that affects the x direction as well. So there's modeling assumptions here which we may be asked about later on, or we may not. So that's just clear, and then you can see the path of the parabola more clearly. We have a y-intercept essentially at the point of projection right here on this illustration. So I'm going to redraw that in a moment. Now, we're given the two equations, and we have to find first the value of k and the horizontal distance traveled by the stone once it hits the ground. So it looks like a complicated scenario, but once we plug in the numbers, you'll see it's actually not too bad. So let's just reconstruct this diagram. Let's just have a look at the parabola itself and try and solve these problems. All right, so what I've done, I've just rewritten the equations. I've just dropped the meters notation. We know we're dealing with meters, and we know that time is dealt with in seconds. So there's the standard units. What I've just done is I've just redrawn the situation. So I've drawn the parabola. This is a Cartesian parabola defined by x and y, but we know that x and y themselves are defined using the parameter t, which represents time. So in other words, you can measure the position of the stone at any point by measuring its time and then converting the time into a horizontal distance and a vertical distance, and that would pinpoint exactly where it is. So there's various things we can do with this. Now, let's suppose we want to find out what the y-intercept is, just before we get into the main meat of the problem. We know initially at the point of projection, the stone is located right here at the top of the cliff. I've just dispensed with the cliff because we don't need it. At that point, the point of projection is where the clock starts ticking. Okay, so we know that at that point t would equal 0. Now, to get the x and y coordinates for that, we simply sub t equals 0 into our two equations. Now that means that x would simply equal 0 because 5 root 2 over 2 multiplied by 0 is just 0. That seems to tell us that this is indeed going to be the y-intercept and the model is working. And also, if we sub in t equals 0 into the equation for y, you will notice that all these complicated terms, the t squared here is 0, the t is 0 here, and we get 25. So 25 on the in the y direction. So that does indeed pinpoint this point here as being the initial point of projection. So that's at with coordinates 0, 25. So you can build the coordinates using the parameters pretty easily by subbing the parameters in. So what we're asked to do in the question is to first of all figure out what this constant k is. So this model is valid between t equals 0 and t equals some constant k. Now, if you look at the path of the stone, it's following a parabola. Now, the parabola is, of course, a quadratic equation, okay? And this parabola would effectively not know that it's being used in a modeling situation. It's just a quadratic. So it would want to continue down here, depending on how it's how it's defined, like if it's defined for all real values of x, for example, or all real values of t, then it would just continue. And similarly, it would continue on the left-hand side as well. It would kind of carry on down here, behaving as quadratics behave. So we have to fix the domain and fix the range of values of t to make it fit this path of the stone, because the stone will stop moving once it hits the ground at this point here. Okay. So what is special about that point? Well, if we look at the situation we're in, that point is an x-intercept. Okay, it's pretty clear that in this situation, the point we're interested in is the x-intercept. And at the x-intercept, we know that the y value will be 0. So to get that point, we simply have to set our y equation equal to 0 and determine the values of t for which that occurs. So let's do that. So, so this is for part A. And you're going to use you can use your calculators for this as well. So when y equals 0, set our equation minus 4.9 t squared plus 5 root 2 over 2t plus 25 equals 0. All right, now to show a bit of working out, to convince the examiner you know what you're doing, we have the quadratic in the correct form. We've got an a value as minus 4.9. So let's just write that down. So we have a is equal to negative 4.9. Okay, the b coefficient is right here. It's positive as well. So it's plus 5 root 2 over 2. So we'll write that in as well. 5 root 2 over 2. And our c, which is right here, plus 25. And we can put that in. C equals 25. And just make sure you've got all the signs correct. So we can now use the quadratic formula. And we're solving for t. So t would simply be minus b. So that would be minus 5 root 2 over 2 plus or minus the square root of the discriminant. Now the discriminant is obviously b squared. So that's going to be 5 root 2 over 2 all squared. Now don't worry about this because we're going to use the equation solver on the ClassWiz to do this. We're not going to have to input all this by hand. So that's b squared subtract 4 multiplied by a, which is negative 4.9. And I didn't make my square roots long enough, but never mind. Multiplied by c, which is 25. And that's going to be all over 2a. So that would be 2 lots of negative 4.9. Okay, so we've got the working out complete. I'm just going to extend that as well. Right, so at this point, you'll think, okay, I don't really want it. That's quite a lot to plug in. So we get our ClassWiz, and we're going to use the equation solver. So just to recap what to do here for your equation solver, if you go to menu on your ClassWiz, okay, just use the arrow key, go down to x, y equals 0. That's the equation and functions. Press equals. This is a polynomial, so that's option 2. The polynomial degree, remember the degree is the highest power of x, or the highest power of the variable in your polynomial. So because it's a quadratic, that's 2. Okay, and we have ax squared plus bx plus c. So we plug in our coefficients for a, b, and c. Don't worry that it's an x variable. That's just a standard. We're going to call it t in this situation. So we put all our numbers in. So we have negative 4.9, press equals, that will go in. We're going to have 5 lots of root 2. Okay. Over 2. Not sure if that's going to go in correctly. I think that's right. And then plus c, so that's going to be 25. And let's see what we get. So we get one solution at 2.648, and we should have a second solution at negative 1.926. So now we can write down our solutions. Now, if we notice, we've got a negative solution. Now, the negative solution we obviously dispense with because t is defined for greater than or equal to 0. So that falls outside our range. This would be a solution, again, if all values of t were allowed, and it would occur where this parabola would cross the x-axis over here. Okay? That's not what we want. That's not the modeling situation. So we dispense with that. We ignore that answer, and we're just interested in the first answer, which was, I'll just go back to it. It gives you all this other information. So that's 2.648. All right, so let's just write that down. So this is t. So therefore, t is equal to 2.648. Seconds, and we'll leave that to 3 decimal places. Now, have we found our constant k? Well, yes, we have. Because we've just identified this point as having a parameter value t of 2.648 seconds, that's the point where the y value is 0, okay? And that's where the stone ends its parabolic motion. So the k value, we'll just confirm this, and I'll just partition the screen so we've got a bit more space. So we now know that the k value is equal to 2.648 to 3 decimal places. All right, so I hope that makes sense. It's just putting all these different ideas together. So that was all part A. Now for part B, we have to find the horizontal distance it's traveled in that time. Now, if we look at the diagram again, the horizontal distance, obviously it starts at 0 and it moves to the point there that I've just highlighted. So if we sub in our parameter value that we've just obtained for when y equals 0 into the x equation, then we'll get the horizontal distance it's traveled also. So this is basically, it's a very, very simple process. It's just subbing numbers into the equations, essentially, or setting the equations equal to certain values, which are things we can do. It's the modeling that makes it a little bit more complicated. So you have to kind of unpick what you have to do from the context of the question. So let's state when t is equal to 2.648, okay, x is going to equal 5 root 2 over 2 multiplied by that number which we've just found, so 2.648. Okay, so if I just on my calculator just do this, just cancel all that, let's go to the normal operations. So we have 5 root 2, let's come out of that, over 2. Okay, and then multiply that by 2.648. This will give us the horizontal distance. So, and this is in meters. So this is 9.36 meters. So therefore, we'll do that to 3 significant figures. It doesn't specify the accuracy. I mean, in an exam situation, you would use 3 significant figures. I just kept it at 3 decimal places just to make sure the accuracy is there. So what you could now do is restate your value of t to 3 significant figures as well, if you wanted to, which would be 2.65. So that's essentially that question done. When you're doing these modeling questions, if you're given a diagram or which is quite illustrative, or if you're not given a diagram at all, it is a good idea to draw a diagram. Okay, so let's have a look at the next example. So in this second example, we have the motion of a figure skater represented by 2 parametric equations. And you'll notice the parameter is time again, and time is defined from the point in which the clock is started. So t has to be greater than or equal to 0. The parametric equations are defined using trigonometric functions, as you can see. And we've got the graph plotted for us on the right hand side. So we've got a diagram which we can use as a reference point. The x component of this is measured in meters, so and the y component is measured in meters. So the Cartesian grid is essentially a bird's eye view of the figure skater's path. So for part A, we're asked to find the coordinates of the figure skater at the beginning of his motion. Well, at the beginning of his motion that's obviously when the clock is started. So we know that's when t is equal to 0. Okay, so that's the first thing. Now, if we plug t equals 0 into our 2 equations, which I'll do, and just for the sake of space, I'm just going to do this in the empty space provided up here, and we'll move down the page shortly when we move on to parts B, C, and D. Okay, so for part A, at the beginning of motion, t is equal to 0. That's the value of our parameter. And to get the coordinates, we need to sub that into x and y. So therefore, x is going to equal 8 cos of 20t. So in other words, 8 cos of 20 multiplied by the 0 that I just substitute in. Now, you'll be familiar with the cosine of 0. So 20 times 0 is, of course, 0. If you take the cosine of 0, that's going to give us 1. Multiply that by 8, we're just going to get 8. So that tells us that the x coordinates at the start of the motion is when x equals 8. So we can just sort of cross-reference this with the diagram. So over here, that's where x equals 8. So it looks as though if we just plot a vertical line on here, just to see what it's doing. So it's about there. It seems to be at one of these extreme points on the right hand side. So it's going to be either the top one, which I'm just highlighting here. So it's going to either start motion here, or it's going to start motion here. So I should say it's a figure skater. So it's going to start either at one of those two points. So let's find out by subbing in t equals 0 into the equation for y, where this location actually is. So when y equals 0, when t equals 0, y is going to equal 12 multiplied by the sine of 10 multiplied by 0. And then we have to subtract pi over 3. Like so. So obviously running out of room here. So I'm just going to drop down to here. So if we do that, we're going to have y is equal to 12 multiplied by the sine of essentially negative pi over 3. All right. Now you can do that on your calculator. If you plug those numbers in, which I've already done, you're going to get 6 root 3. Sorry, negative 6 root 3, which is approximately negative 10.392. All right. Now, that seems to correspond nicely with the diagram. So we know this is a negative value now, negative 10.392. So it's going to be this point here. So this is where the start of this circuit begins. So this is the starting point. Okay, and because t is defined as purely greater than 0, this could carry on ad infinitum, yeah, forever and ever. So there's going to be multiple circuits going on if we have a domain like that, purely positive values of t. So for part B, we have to find the coordinates of the point where the figure skater intersects his own path. Now, this is quite an interesting question. Because we have the diagram, it makes this a little bit easier. But we can see clearly there's just one point on the diagram where the figure skater intersects his own path, and it's right here. Now, it appears to be at the point where x is equal to negative 4 and y is equal to 0. So I'll just make a note of that. So it looks like it's at negative 4, 0. But we have to find, we have to sort of verify this really. So it says, find the coordinates of the point. Well, just writing them down isn't really good enough. But we can tell from the diagram that it's definitely on the x-axis. So we can see clearly. So that's questionable, but we can see that y is equal to 0. It's not 100% clear that it is bang on negative 4. So what can we do? How can we verify this? Well, we could look at the x values. Now, if we look at the x values, let's suppose we assume that x is equal to negative 4, which we're not 100% certain on. We know that if I just draw a line down through negative 4, I'm just going to make it look a bit better. So about there. If we do that, you can see that there's actually 3 points of intersection. There's the one I've just highlighted, and then there's a point here in the top left quadrant and a point here in the bottom left quadrant. So we're actually going to get 3 possible values, okay, for t. Now, that's not very useful, really. That means we'd have to look at all 3 cases separately. However, if we consider the y direction, I'm going to do the same thing in the y direction. We only have 1 point of intersection when we have y equals 0. I'll just label that. So that's y equals 0. So we have 3 points of intersection when we consider x is equal to negative 4, but we only have 1 point of intersection when y is equal to 0. So if we set y is equal to 0, we should just get that key point, and then we can generate the x coordinate from that and hopefully verify that it is indeed negative 4. So we're going to do that next. All right, so I need a bit more space to do this. So we're going to set y equal to 0. I'm going to verify that we actually get negative 4 for our x coordinate. All right, so when we set y is equal to 0, remember we only had 1 point of intersection, which is good. So let's see what happens. So if I set y is equal to 0, the equation is going to be as follows. So it's going to be 12 sine of 10t subtract pi over 3 is equal to 0. Okay, so we have a trig equation. And remember, of course, that t is greater than or equal to 0. So we have a trig equation format similar to what you've done previously in chapters 6 and 7 and also in year 1. So what I'm going to do now is just to make things a little bit more simplistic. We're going to I'm going to call it big T1 because we're going to be doing more of this later. So big T1 is going to equal 10 little t subtract pi over 3. Okay, so rewriting the equation now, we have 12 sine of big T1 is now going to equal 0. Now, obviously 12 can't equal 0, so therefore sine of T1 is going to equal 0. Now, if that's the case, let's just work out our principal angle. So the T1 will be equal to the inverse sine of 0, and that's just going to equal 0. Now, we can add this to a cast diagram, and I'm doing this because I want you to see how this behaves. So on a cast diagram, just put it down here. We've got C, A, S, and T. And I'm going to cheat a bit. I'm going to make 0 actually look like an acute angle, just so it's clear. So because 0 doesn't have a sign as such, it doesn't actually matter which quadrant we put it in, which is quite interesting. So if I put this angle here, 0, and the fact that this value here is neither positive nor negative, you'll see that it actually won't matter. So if we add it to the cast diagram, I'm going to put it in where sine is positive. So if we do that, we're going to have 0 degrees there, or 0 radians, I should say, and 0 radians there. And reading off the values for T1, we'll get the following. We'll get 0 radians, and then pi minus 0, so that's pi. And note, if I'd have put them in the opposite quadrants, T and C, you would get the same values. Okay, and then you would also get 2 pi, 3 pi, and all natural number multiples of pi. Okay, so that's what T1 would give us. Now, if we replace T1 with 10t subtract pi over 3, so that's what we're going to do now. So 10t subtract pi over 3, we have an infinite sequence of solutions for this. So it would be 0, pi, 2 pi, 3 pi, etc. So we simply add pi over 3 to all of them and then divide by 10. So let's do it in stages. So 10t would be pi over 3 and add pi over 3 to pi. So that's going to be 4 pi over 3. Okay, and then add pi over 3 to 2. It's going to be 7 pi over 3. 2 would be 6 pi over 3. And you can see the pattern here. I mean, if you don't want to have to work them all out, you notice that we're adding 3 pi each time. Okay, so then you would get 10 pi over 3. Okay, 3 pi in the numerator, I should say. It's not. It's you're adding pi each time because it's 3 pi over 3. Now then, for t itself, we're going to divide all this by 10. So we're going to get pi over 30, 4 pi over 30, and I'm aware that that will simplify, but I'm just going to leave it like that. 7 pi over 30 and 10 pi over 30. And these are all in seconds, and there will be more to come as well. So those are the possible times when the figure skater intersects his own path. Now, when does this happen? Does the figure skater intersect his own path at the same point on every circuit? Well, we can just verify this now. So we've got the parameter values. Now, if we sub those into our x equation, so x is going to equal 8 cosine of 20t. So that's going to be 20 multiplied by, we'll put our first result in, so that'll be pi over 30. Okay. Now let's just do that. I'm just going to do this on the calculator just to show you. So go to option 1. So 8 multiplied by the cosine of 20 multiplied by pi over 3. I'm just going to close the brackets. Okay, so we get -4. So the diagram looks correct. So this is equal to -4. Okay. Now then, if we add 3 pi to our time, 3 pi over 3, I should say, the next solution is going to be at 4 pi over 30. So let's try that. So if x is equal to 8 cos of 20, and then we're going to multiply that by 4 pi over 30, which is our second solution. Then what's going to happen here? Well, let's do that. So I'm just going to edit my calculation slightly. So just going backwards. So I'm just going to change that to 4 pi there. Come out of that, and then we can just press equals. So we get -4 again, which does check out. So this is the x coordinate where the figure skater intersects his own path. All right, so now looking at question 2, part C, we have to find the coordinates of the points where the path of the figure skater crosses the y-axis. So the y-intercepts. Now, looking at the diagram, we've just verified the x-intercept at -4, 0. Now, the y-intercept, we have 4 points of intersection. Now, this means that we're expecting four solutions to this. Four unique solutions. In the previous example, we had, obviously for the times, we had an infinite string of solutions, but they would all generate -4 for the x coordinate because it's where the skater intersects his own path. It's the same point every time. Here we've got 4 unique solutions. So to find the coordinates where the path of the figure skater crosses the y-axis, a y-intercept, if you like, we obviously have to set x equal to 0 in this instance. So that's what we're going to do next. Okay, now you'll have a bit more space than I do, so I've just scrolled down the page again. Now we've just sort of outlined our approach for this question. So I've just written down the information we have. So for the y-intercept, x is equal to 0. That means that we have to set 8 cos 20t equal to 0. And we're interested in 4 solutions, four unique solutions, really. Okay, and that's all we should get. So after we got the 4 unique solutions, they will probably repeat. And just remember that t is going to be greater than or equal to 0. Okay, so we do have an infinite string of solutions. Should we need to write them down, which we don't, which we can't, in fact. So looking at this equation, 8 cos 20t, well, clearly the 8 can't equal 0. So we just need to focus on the cos of 20t being equal to 0. So again, as is customary, I'm going to make a substitution. So I'm going to say we'll call it big T2 this time. We've just done T1 equal 20t. And what does that give us? Well, this means that we've got cos of big T2 is equal to 0. So now we can find the principal angle. So the principal angle well, we just have to do the inverse cosine of 0, and it's whatever the calculator would give us. Now, if you know a bit about the cosine graph, cosine is 0 when the angle is pi over 2, so 90 degrees. So that's when it crosses the x-axis. All right, so that's our principal angle. Now, again, because the value is neither positive nor negative, it will make absolutely no difference whatsoever which quadrants we put our principal angle in, because it's pi over 2. So I'm just going to draw it out again. So we've got C, A, S, and T. And it's pi over 2. So again, doesn't matter. I'll just put it where cos is positive. So here and here. So I'm just going to add them on. And I realize it's a 90-degree angle. I'm cheating a bit here. But I think it just helps you get your head around the calculations a bit more. All right. So T2, reading off. Well, remember 0 starts here and we go anti-clockwise in the positive direction. So that means that because T is greater than or equal to 0, so would T2 be, obviously. So we're going to have a first solution at pi over 2. There can't be any negative answers for this. And then the next one will be at 3 pi over 2. In other words, 2 pi subtract pi over 2. Now, we need 4 solutions for this. So I can't just stop there. So then we have 2 pi plus pi over 2. So that's going to be 2.5 pi over 2 or 5 pi over 2 for the next one. Going round again. And then we have 4 pi subtract pi over 2. So that's going to be 7 pi over 2. And you'll notice again in the numerator, we're just adding 2 pi each time in this instance. So once you've spotted the pattern, you can just do that. Okay, that's only 2 pi in the numerator, of course. You're not adding 2 pi, you're adding pi, but that's how it looks in the numerators anyway. All right, so we've got our T2s. Now we can replace the T2 with 20t now. So therefore, 20t is going to equal all the same stuff. So pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, so you're adding 2 pi in the numerator each time, and we could go on with that, but we've got 4 solutions there. Now we have to divide by 20 to get our t values. So t is going to be pi over 40, 3 pi over 40, 5 pi over 40, and lastly 7 pi over 40. Okay, so now we've got that, we can just substitute in each of these 4 solutions. So we've got solution 1, 2, 3, and 4. Now these are the 4 values of t, the time when the skater is crossing the y-axis. So let's have a look at case 1. So case 1, where we have t is equal to pi over 40. So we're going to sub that into our equation for y now to find out where it crosses the y-axis. So y is equal to 12 sine of 10 multiplied by the pi over 40. Okay, and then we have to subtract pi over 3. And we find out what that's equal to. So we're going to plug those into the calculator. So we have, first of all, 12 multiplied by the sine, open a bracket straight away. So that's going to be 10 multiplied by, I'm going to open a bracket again. So that's going to be pi divided by 40. Okay. Close that bracket. The bracket nested inside the other bracket, that's what we've substituted in. And then we're going to subtract pi over 3. So that's divided by 3. We could write it as a fraction if you wanted, it doesn't matter. Close the bracket and let's see what we get. Okay, so we get a rather nasty looking surd there. So I'm just going to change that to a decimal. So the first solution is going to be at negative 3.106. So we'll do this to three significant figures, I think. So that's negative on there, sorry, negative 3.11. Okay, and that's meters. We'll say that's to 2 decimal places. Okay, so that's our first solution. Now we'll check this on the diagram in a moment. Now, obviously that's a lot of working out. So just to skip this a little bit, and you can write it out in full if you wish. So solutions number 2, 3, and 4. Obviously we're plugging in exactly the same stuff. The only thing that we're changing is the value here. So we've done pi over 40. In the next case, we're going to be looking at 3 pi over 40, then 5 pi over 40, and then 7 pi over 40. So just to save a bit of time in the video, but you can write it out if you want, I'm just going to write out the solutions, and all we have to do is just edit this calculation ever so slightly. Okay, so going back to the calculator, so everything is pi over 40, so I just have to put a 3 in there, and let's see how that changes our answer. So change that to a decimal, so we get 11.59. So that's 11.59 to 2 decimal places. And these are meters. Okay. Then for solution number 3, it's 5 pi over 40. So I'm just going to edit my calculation. And just delete that and change that to 5. Press equals. Change that to a decimal, so we get a positive version of what we got in solution number 1. So it's going to be 3.11 meters to 2 decimal places. Okay, and solution number 4. Again, just editing the video, editing the calculation. So 5 pi over 40. I'm going to change that to 7 pi over 40. And what do we get here? Okay, so this is the negative version of 11.59, as we probably could have predicted. Two decimal places. Okay, so those are our 4 solutions. Now, if you're interested, just to check whether these are indeed the only 4 solutions, remember T could have an infinite number of solutions. So just arbitrarily, I could add the next one. You can see that the pi's are increasing by 2 in the numerator each time. So the next solution, looking at this, would probably be 9 pi over 40. So if we, just for the sake of argument, and then there'll be more after that, if we put 9 pi over 40 into our calculation, so just going back to this, just to show you that this is indeed, these are indeed the only 4 solutions. We change that to a 9 and press equals. We get the first solution back. Okay, so we're going to go through the cycle of negative 3.11, 11.59, 3.11, and negative 11.59 over and over again. Okay, so those are our 4 y-intercepts that we've just calculated. Okay, and for the last part of this question, we're asked to determine how long it takes the figure skater to complete one full figure of 8 motion. And I've just indicated on here the coordinates for the y-intercepts. All right, just so you can verify those. Now, if you remember back to answer question part D, if you remember when we did part B, we looked at the coordinates where the figure skater intersected his own path, and we found 4 times in which that happens. Now, if we just sort of apply this to the diagram, we determined in part A that the figure skater begins his skating at this extreme point on the right-hand side, which I'm just going to highlight now. And we found out where that point was. It was right here. Okay. But we don't have to think of it as a figure of 8 motion starting at that point. We can choose any arbitrary point along the path and just find out how long it takes for the figure skater to return to that point in the cycle. Now I'm going to use the point of intersection of his own path. So if we look at that, I'm just going to highlight that in purple. So that point there was at -4, 0. But more importantly, this occurred at these particular times. So the times are measured in minutes. So starting from the green point that I've highlighted here. Okay, now follow the journey around as I'm going to do now. So he starts here and then he moves along a path, presumably this way, I don't know. And then after pi over 30 minutes, he reaches the x-intercept. So that's pi over 30 minutes has elapsed. Okay. So that's important. Now, if he continues on the jet, I mean, it could be in the opposite direction. I'm just using this as a one variation of what could possibly happen. After pi over 30 minutes, he continues from this point here. He goes around this loop, and then he returns back to that point. So that means that the second part of the journey, by the time he gets to that point again, the amount of time that's elapsed in total is 4 pi over 30. So if I just do a little key here, the total time for this pink path that I've highlighted would be 4 pi over 30 minutes. All right, but let's suppose we're just interested in the loop in the top half of the plane. So if I just go over that, this part here starts at pi over 30 and returns to the original point at 4 pi over 30. So for that path, the amount of time that took is going to be 4 pi over 30 minutes, subtract the pi over 30 minutes, because it took pi over 30 minutes to get to the starting point right here in the first place. So that's going to equal, and I'll just put the equals over here. So if you do 4 pi over 30, subtract pi over 30, that is, of course, 3 pi over 30, which is just pi over 10 minutes. So that tells us that the upper branch, this path here that I'm just going over again, took pi over 10 minutes. Now we can just check that the bottom loop would take exactly the same amount of time. By the time it gets to the x-intercept again, which is right here, I'm just going to go over it again. That's a total of 4 pi over 30 minutes. Now the journey is going to continue. He's going to carry on along here, go back through the original starting point, and then get back to there. Right, now if we look at the next two solutions, the starting point of that journey took place from 4 pi over 30 minutes, and then he returned back to that point at 7 pi over 30 minutes. So that part of the journey is going to be as follows. So it will be 7 pi over 30, subtract 4 pi over 30, which is also 3 pi over 30, which is pi over 10. And that's in minutes. So what that means is that for each of those upper and lower branches, the skater took pi over 10 minutes to complete each of those circuits. Now those upper half and lower half circuits. Now, if that's the case, to complete the full figure of 8 motion, we just have to combine these two times. So we've deduced it just diagrammatically by thinking through how much time it takes for him to pass through that x-intercept. Okay, so for part D, total time for one full figure of 8, or that's hyphenated, motion is, and we'll just add those together, so that's going to be pi over 10 plus pi over 10, which is equal to 2 pi over 10 minutes. And you can simplify, oh, that doesn't look very good, minutes. You can also simplify that to pi over 5 minutes. Now, there's different ways of doing this. You could look at the period, for example, of the equation for x. All right, you could use that, and also use things like the lowest common multiple. Essentially, if you compare the period of x with the period of y and find out where they coincide and look at the lowest common multiple, you'll also get 2 pi over 10. I just think looking at the diagram and then working out the times for each of those half loops is a little bit more intuitive, I think. So anyway, I suggest you try some of the questions out that follow on from this example. But other than that, that concludes parametric equations. They will be reoccurring in differentiation, and do practice the examples, go over them again and again, because they are a feature of the main exam.